Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I'm one of the co-founders here, along with my younger brother, AJ Raj. As you can see today, we have a new Algebra 2 lesson, and we're just going to be continuing with standard deviation. In the last video, what we did was pretty much found standard deviation. We learned how to actually calculate it, the formula, along with the procedure on the TI calculator, and we also learned the definition of what standard deviation is and what it means when we say standard deviation is a measure of variation. So again, standard deviation falls under statistics, which is our focus right now in Algebra 2, in our Algebra 2 course. Today, however, we're going to be interpreting standard deviation. So what that means is we're going to be understanding when we find the standard deviation of a data set, what does it mean? So if we have a large value representing the standard deviation, or we have a small value representing the standard deviation, what does that mean in regards to the data set? How does that characterize the data set in another way? That's another way to put it. But that's what we're going to be understanding today. And if you see here, I've just thrown up an image. This is the actual formula for calculating standard deviation. So SD stands for standard deviation. This can also be represented by the symbol sigma, which is the Greek letter we looked at in the last video, is equal to the square root of the summation of every value in the data set minus the mean squared divided by the number of values in the data set. So keep in mind, what we first do is we calculate the mean of the data set. Mean is very important for finding standard deviation. Then we take every value in the data set, we subtract the mean from it, and then we will square each of those subtracted values so that we don't have any negative numbers. Then we have this E symbol here. This is the summation symbol in math. You pretty much will add all of those values together and then divide by the number of values you have. Finally, you'll take the square root and you'll get the standard deviation. You can also do this on a TI calculator. And our goal today is to understand what small and large deviations mean, and then we're going to look at an example that involves some students' test scores in a class so that you can see a real-life application of how standard deviation would come into play. So before we get into the video, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. So let's jump into the first slide. Let's understand what small and large deviations are. But before we even do that, let's review what standard deviation is. So remember, standard deviation is a measure of variation, and it tells us how spread apart our distributed data is. By spread apart, we mean how far apart are the data points from one another. Are they close to each other in value? Are they more variable? Are there more outliers? Are they more spread across the number line? That's what standard deviation tells us. It's a measure of distribution, spread, whatever you want to call it. And then what we do is when we find standard deviation, we're going to then determine, is this a small deviation or a large deviation? Let's look at what those definitions mean. So small standard deviation. Small means tiny in a sense. And when we compare it to data values, a small standard deviation is going to indicate that the data that we have in the set is clustered tightly around the mean. So what does that mean? Well, the mean is the average or the norm, and it usually falls somewhere in the middle of the data set. It's not equal to the median, which is the middle of the data set, but it falls somewhere in the middle because it's the average. If we plot it on a number line and then we plot all the other data values that are in this set that we've been given, when we have a small standard deviation, it means that these data values are very close to the mean. That means clustered tightly or clumped, if you want to think clumped together. Like when you're holding someone really close to you, you're both very close to each other. So that's like these data points are very close to the mean. You can think of it that way. For example, if we have the numbers 5, 6, and 7, let's say 6 is the mean of some data set. Well, the points 5 and 7 are very close to 6, so they're clustered very tightly around the mean, and the standard deviation is pretty small. On the flip side, we have a large standard deviation. So when we compare it to data values in a set, this will indicate that the data is more spread out. That means that instead of being clumped around the mean, the data points are going to be more scattered throughout the number line if we were to plot them. For example, if again our mean was 6 and then we had the numbers 3 and 9 in the data set, those are a bit farther away from 6 than 5 and 7 were. So the standard deviation in this set of numbers is larger than the standard deviation in the previous set of numbers. So it just indicates that the data is more spread apart and farther away from the mean. With that being said, let's jump into deviation of data. So how do we interpret when we get a deviation, like when we calculate the standard deviation, what do we do with it? So all values fall within some number of deviations from the mean. So what we do is we calculate what the mean is, we'll plot that, and then all these values in our data set are going to fall at some value, some number of deviations from the mean. So you're going to calculate the standard deviation, you're going to add that to the mean, and then you're also going to subtract that from the mean. And then it's almost like this is the mean, you're moving right a step and you're moving left a step. You can think of it that way. And that whole step, those two steps you took, that encompasses one standard deviation from the mean. So what this is saying is that all values in a data set, in a given data set, when we plot them on the number line in relative to the mean, they all fall in some number of deviations from the mean. Maybe all the numbers fall within one standard deviation of the mean, meaning they're pretty close to each other. Maybe they all fall within 5 standard deviations of the mean, meaning they're a bit farther away from each other. That all depends on the value of the standard deviation, of course, but that's what this statement is saying. Values within one standard deviation of the mean are the values that fall from one standard deviation below the mean to one standard deviation above the mean. So what does that exactly mean? So when we have the mean of a data set, or the average, what we do is we calculate the standard deviation like I just said, and we're going to add that standard deviation value to the mean to find one standard deviation above the mean. That's what it's saying. Then we're going to take that standard deviation value and subtract it from the mean to get one standard deviation below the mean. And when we add it and we subtract it, that whole range of values, let's say this is the mean, this is me adding, and this is me subtracting, so me finding values above and below one standard deviation from the mean, this is all considered one standard deviation. Similarly said, the same is true for 2, 3, and more standard deviations from the mean. So we can actually have multiple standard deviations. After we find the first one, whatever is the value that we found, let's say we have the mean and we added the standard deviation, we found a new value that sets like the range for the upper standard deviation. We can add the standard deviation again and again and again, and then we can subtract the standard deviation again and again and again until we find the amount of standard deviation standard deviations it takes, so that all of the data sets fall within like the ranges that we are creating of standard deviations. So it might be kind of hard to explain or hard to understand right now, but trust me, you'll get it after we go through this example. So we're going to do example number 3. We did the previous 2 examples in the first video, so go check that out if you haven't already. And this is going to be on student test scores in class. So here's kind of setting the scene. The following that you're going to see is a set of test scores for one class. We're going to find the mean and standard deviation of this given set of test scores. Then we are going to draw a number line, a simple number line. Hopefully you remember those from like pre-algebra, algebra 1, even before that. And then we're going to plot the data values of the test scores, and then we're also going to plot the mean with them. Afterwards, we're going to mark off the standard deviations on either side of the mean, like I was just talking about. Our final question that we're trying to answer is within how many standard deviations do all of the values fall? So here are the scores that were given: 87, 85, 85, 68, 92, 97, 97, 95, 76, 83, 92, 70, 55, 98, 85, 95, 77, 72, 83, and 79. They're not in order. We'll order them when we solve this. They're purposely not given in order, but these are all the test scores we're given, these student test scores, and we have to find the mean and standard deviation. Then we have to draw a number line, plot all of these values, and plot the mean. Then we have to mark off the standard deviations on either side of the mean. So the first standard deviation, second, third, etc., however many we need. And then we need to make sure all of these values fall within those standard deviations. And then we finally report how many standard deviations do all the values fall in. If we have a large standard deviation, that means these kids scored a wide range of test scores. If we have a smaller standard deviation, they all performed about the same and they're clustered around the mean. So let's look at the solution, which I've actually already done for you because it's a lot of work. So just take a look at it. Again, example 3, student test scores. So what I did here was I first drew out like a number line. You can see that it has n marks here, and I'll explain why we have those. So our mean was x bar, which represents mean, is equal to 83.5. So that goes right here in the middle of our number line. Then what we're going to do is, after calculating this, obviously you can use a calculator, add all those values together that you were given on the previous slide, then divide by the number of values, and you'll find the mean pretty simply. Or you can just input them in your stat window, and then you can actually find the one variable stats for all of them, and you can also calculate the standard deviation that way, which is what I did. So I input all these numbers like I showed you in the last video, so again, check that out. I found the mean, which is 83.55. I found the standard deviation, which is 11.6. So what you first do is you're going to plot 83.5 in the middle of your number line. Then I just wrote out all of the numbers of the test scores. So all these numbers that my laser is following, these are all of the test scores. These are all of the test scores. Then what I did was I started with the mean. I added the standard deviation to it, so 83.55 plus 11.6, and then I got 94.71. So this is one standard deviation above the mean. I did the same thing, but I subtracted next. 83.55 minus 11.6, and then that is equal to 72.39, which is one standard deviation below the mean. And then I'm just seeing which values of the test scores fall within 72.39 and 83.55 and 83.55 and 94.71. And then all of these values fall within those. So all these values are within one standard deviation of the mean. Well, we still have values out here and we still have values out here. So what do we have to do? We have to add 11.6 again to 94.71. If we do that, we'll get 105.87. And we have to do that again on the left side because we have all these four values out here that don't fall in the standard deviation we found. So we're going to subtract 11 point. This is one. I think this is 1/6, but we're gonna subtract that from 72.39, and we are going to get 61.23. So this is actually supposed to be 11.16. I guess I wrote this wrong, so just keep in mind that's 11.16. So then we get 61.23, and this is going to be our second standard deviation up here, and our second standard deviation over here. However, you think you're done. You think it's just two standard deviations, but we have a 55 over here. So we actually have to do one more standard deviation. So we're going to subtract 11.16 again from 61.23, and we got 50.7, and 55 does fall in that range. So we got our third standard deviation. Just keep in mind that we actually don't need to add a third standard deviation to this side, but since we are subtracting from the left side, it's almost like an equation. What you do to the left side, you have to do to the right side. So I had to add another 11.6 and get a third standard deviation up here of 117.03. So with that being said, we've had one standard deviation, which was the first time we added and subtracted 11.16. Then we had a second standard deviation when we added and subtracted 11.16 again, and then we had the third one where we had to include 55. So we had three standard deviations, and the answer is all values fall within three standard deviations of the mean. That's how you would solve that. I hope you enjoyed this video. It was pretty brief because we'll probably go into more examples in the following videos, but I do hope you enjoyed it. If you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Make sure to check out our website and our Gmail as well to support us, and thank you. I'll see you in the next Algebra 2 video.